Alright, hello everybody. So here's the next Physics 232 YouTube video. What I want to do in this video is to, first of all, just summarize what we discussed about some possible nonlinear fit strategies. And then after that, what we can try to do is see if we can come up with some kind of intuitive interpretation of what the value of chi-squared tells us. Does that tell us anything meaningful? Okay, so first, the nonlinear fit summary. So step one is to find the best fit parameters. And one way that we thought about doing that was to set up a grid of parameters and evaluate chi-squared at each grid point. Okay, so the point that results in the minimum chi-squared value chi-squared value gives an estimate of the best fit parameters. So as a picture, what that looks like, if we had a two-parameter fit, for example, maybe this is the A1 axis and A2 axis. Those are your two fit parameters. Then this is the minimum value of A1. This is the maximum value of A1. And same thing for the A2 parameter. And we set up the grid by selecting step sizes for each parameter. And so for A1, the spacing between these vertical lines is your delta A1 choice. And then we have a spacing between your A2 parameters, and that sets up your choice of delta A2. And then at each one of these grid points, we're going to calculate chi-squared, and one of them is going to give us the smallest value of chi-squared, and that is what we'll select as our best fit parameters. Just one thing to mention is if you found that one of your, where your best fit parameters fell, like where you got the lowest value of chi-squared was somewhere on the boundary, that would be a bit of a red flag, because what you might think is, well, what if I made A2 a little bit smaller? Is chi-squared going to decrease again? And so generally what you don't want to see is that your best fit parameters are up against the boundaries of either A1 minimum or maximum or A2 minimum or maximum. Okay, so what you want is your best fit result to be somewhere inside of the grid, not at the edge. So this is maybe where your chi-squared minimum occurs or something, and so that would result in, say, your A1 star value, your best fit value for A1, and your A2 star value. Okay, so step two is to estimate the uncertainties on those parameters. So you pick one of the parameters say A1 for example, and evaluate chi-squared at 3 values of A1 that bracket the minimum in chi-squared. And so what you have to do is you have to pick your 3 values of A1, where if you were to plot how chi-squared changes with A1, you want to be in the region where it looks quadratic. So you expect chi-squared to vary quadratically near the minimum. Okay, so what we could do is we could set up a plot that looks something like this. And so say this is your jth parameter and this is your chi-squared axis. What you want is you want to get in a region where chi-squared looks quadratic. So here chi-squared is going to be proportional to aj squared. Okay, and then you pick an aj value and you say that you get chi1 squared at that point. And then you shift over here by an amount delta A, so this is, say, delta A, and you calculate a second value of chi2 squared, and then you take the same step size and you end up over here, so this is aj plus 2 delta A, and you go over here and you have a chi3 squared value. All right, so what we found is that we could, in this case, estimate the uncertainty in the aj parameter using root 2 times the step size divided by the square root of chi1 squared minus 2 chi2 squared plus chi3 squared. So when you look at this, you might say, well, that's weird because the uncertainty depends on the step size delta A, and maybe I could make my sigma arbitrarily small by choosing a small step size. Well, what will happen is, in that case, the denominator, which are calculated from the chi1 squared, chi2 squared, chi3 squared, it will scale in proportion to delta A. So if you increase or decrease delta A, you'll get the same approximate increase or decrease in the denominator. And if you made an appropriate choice for delta A, your sigma j should be independent of that value to a good approximation. Okay. So that's that summary. So what I'd like to try to do is, well, actually, maybe I should just mention that I will likely post the Physics 232 assignment number 6 on the course website. You should try it, but we're not collecting solutions and it's not going to be graded. But assignment 6 is all about trying to put this estimate of the uncertainty of your fit parameters into practice. Okay, so the next thing I wanted to do in this video is I wanted to develop, hopefully, an intuitive understanding of the meaning of chi-squared. And so I'm not going to try to pass this off as a rigorous discussion. Rather, I want to see if we can do a qualitative discussion, or mostly qualitative, and to see if we can gain some insights through that. So the definition of chi-squared, and this is something we've used a lot recently, is that it's the sum of the square of the deviations, so the ith measured value of y, minus the calculated value of y from the model when x is equal to xi, divide by the uncertainty, and then square it, and then you add them all up. Where we assume that we've measured xi and yi plus or minus sigma I for I is equal to 1 to n. Okay, so y of xi is the expected value of y calculated from our theoretical model. So, for example, what we might have is some theory where we have some dependence of y on x, and maybe our theory predicts this kind of behavior. And then we go and we make some measurements, some experimental measurements, and we want to get some kind of measure of whether the model captures the features in the experimental results. Okay, and so when we're talking about chi-squared, what we're really doing is we're trying to measure the deviation between, so this is yi minus y of xi, where y of xi sits here, and the measured value is yi, and then down here is xi. Okay, so on average, we would expect that the data should deviate from the model prediction by something that's close to sigma I, right? We wouldn't expect that we're doing a perfect experiment where there's no uncertainty and the data always lie exactly on top of the model prediction. There's always going to be some fluctuations, and I mean, after all, what the Gaussian distribution does is it characterizes those fluctuations. So the width of the Gaussian distribution characterizes those random fluctuations, and that's what sigma represents. So if this assumption is correct, what we're really doing is we're assuming two things. So one is that we've made reasonable estimates of the sigma I values. So if, for example, sigma I has been way overestimated, then you would find that the deviations between your measurements and your model would be small compared to your overestimated experimental uncertainty. The other thing that could happen is maybe the theoretical model that you have doesn't actually explain all the features in the data. Maybe your model's incomplete. So if we expect on average that the deviation should be sigma I, the other thing we're assuming is that the theoretical model used is valid. Okay, so if those two assumptions are true, then we should expect that so for each of the I measurements, if the deviation is about sigma I, then what we have is sigma I over sigma I squared, which is 1 on average. Of course, for some points, maybe we do get a measurement that falls very close to the line, and this difference will, or this deviation divided by sigma will be small. But then there's maybe other points where the deviation is a little bit large, and on average, those two effects cancel out. Okay, so that means chi-squared, which is the sum of this quantity for all n of our measured data points, ought to end up being approximately 1 plus 1 plus 1 plus 1 n times, and we should expect chi-squared should end up being something close to n, the number of measured data points. This is the number of measurements. So, assuming that sigma I is reasonable, if chi-squared is about equal to n, then we should conclude that our model captures the features of the data. And in that sense, what we can do is we can use chi-squared as a goodness of fit parameter. All right, so let's consider a case where our model doesn't capture all features of the data. Let's suppose we have our model prediction that looks something like this, right? So this is our predicted model, and then we go and do the experiment, and what we find is that maybe at large values of x, it looks like the model's doing well, but then for values of x that are small, we find that there's some kind of feature here that's not captured properly by the theory, and there needs to be some kind of revision to the theoretical understanding of whatever the physics is that we're trying to investigate. So in this scenario, points within the red box results in deviations that are relatively large. They're bigger than the sigma I error bars, and so when you evaluate this quantity, you'll get something that's bigger than 1 for all of the points, well, the majority of the points in the red box. And so therefore, when you add up all of the deviations to calculate chi-squared, you're going to get some from the red box that are bigger than 1, and your overall chi-squared will be greater than n, the number of measured data points. So one thing that we could conclude then is a chi-squared value that is significantly greater than n indicates a poor fit to the data. Okay. What about a chi-squared value that is significantly less than n? So how could we get a value less than n if, here, let's write out chi-squared again. So this is the sum of I of yi minus y of xi over sigma I. And we want that to be less than n so that our individual measurements at I have a deviation that is smaller than sigma. So how that could happen is that someone has made an overestimate of sigma I, and we see this in the lab all the time. So let's just finish this sentence and then we'll draw a picture. A chi-squared value significantly less than n usually indicates that the experimenter has overestimated the values of sigma I. So that kind of scenario would look like, here's x and y. Let's imagine that we're doing some kind of linear fit. And what we find is that our data follow this line really pretty good. And so we feel like the model is doing well. But then someone's made error bar estimates like this. So that if you compare the deviation of the data, so this would be like yi minus y of xi, those deviations are really small compared to sigma I. And when you go and calculate chi-squared, you would end up with chi-squared would be, you'd end up with a chi-squared that would be less than n. Okay, so in that case, what you should do is, if you encounter that kind of scenario, I think you should go back and reconsider how you've made the uncertainty estimates in your y measurements. Okay, so the last thing I want to do in this video is I just want to refine that discussion just a little bit. Okay, so expecting chi-squared is about equal to n, assuming you've made good estimates of your uncertainties and you have a model that properly captures the features of the data. So expecting chi-squared equal to n is correct when we have n large. However, what I'd like to do next is let's consider the following extreme cases. So I'm going to consider cases where n is not large. So the first one we're going to think about is a one-parameter fit with n equals 1. So just a single measurement. Okay, so all we've done is we've just made a measurement of x1 and y1 plus or minus sigma 1. Okay, and our model, is a single parameter, and let's just say we expect the result of our measurement to be some constant a. So a is our fit parameter. So if we were to plot our data, we would have our x, y coordinate system, and then somewhere over here we've made, when x equals x1, we've made a measurement of y1, and we have some uncertainties plus or minus sigma 1. Okay, now we don't know what the true value of our fit parameter a is, but let's just assume that it was this red point. So this red point represents the true value of, say, a star. The true value of a, which is equal to a star, for example. Okay, and we, in general, don't know that value. If we did, there would be no point in doing the experiment. Okay, but if we just have a single measurement and we need to estimate the value of a single parameter, all we can do is say, well, the best fit value of a based on the data is a is equal to y1. Right? We can't do any better than that. Our model says y should be equal to a constant. We made a single measurement, and all we could do is say, well, I guess that single measurement is our estimate of this value of a. So this is our unknown parameter a estimated from our single measurement. Okay, so what I want to do with this is I want to calculate chi-squared. So let's just calculate chi-squared. We only made one measurement, so we only have one term in our chi-squared, and it's the measured value minus the calculated value based on our model divided by sigma 1. But our model was just y is equal to a, and we said our estimate of a is just y1, and so what we get is 0. If, on the other hand, we used, so if we use, if, on the other hand, we used the true value a star to calculate chi-squared, and let's say that when we use the true value, let's just put an a subscript on that, we would find, let's see, chi-squared based on the true value would be our measured value minus the true value over sigma 1 squared. And if we look at this, we would expect there to be some deviation between the measured value and the true value, and that deviation should be not so different than sigma 1, and this should come out to be about equal to 1. So what we find then is that chi-squared is artificially low when we calculate it using the experimental data and the value of our model, which is based on the experimental data. Okay, so the issue is that the measured data is artificially set to be close to the parameter value, since the parameter was estimated using the experimental data. The difference between this second calculation, where we use the true value, which in general we wouldn't know, is that in this case the true value is a quantity that's independent from the measurements. And so when you calculate the deviation, it's a sensible calculation. However, when we go back to chi-squared based on an estimate of the parameter, that estimate is not independent of the measurement. The estimate was made using the measurements. And for that reason, the deviation is lower than what you might expect it to be. Okay, let's do another example. Let's do a 2-parameter fit. And the 2 parameters that we're going to use are the slope and intercept of a straight line with n equals 2. Okay, so in that case, what we do is we measure x1 and y1 plus or minus sigma 1, and x2 and y2 plus or minus sigma 2. And our model is y equals an intercept plus a slope times x. I mean, you already know that if you have just 2 data points and you want to put a straight line through those 2 data points, well, you can always do that exactly, right? So if these are my data points here, x1 and x2, and here's y1 and y2, and so maybe there's some error bars on these points, right? And so if this is the straight line estimated from the measurements, you can already see exactly that the deviation, say y2 minus y of x2, is exactly 0. And over here, y1 minus y of x1 is exactly 0. And you would go and you would calculate, and this is something you could confirm yourself, you would calculate a chi-squared for these 2 measurements would be equal to 0. Okay, but we could do the same thing we tried to do last time. We could say, well, let's suppose that we somehow knew what the true straight line looked like, and it's not exactly the straight line that we estimated from the data. it is this purple line. And if we did this using, say, y2 minus, say, the true intercept plus the true slope times x2, that would be about equal to sigma 2. And over here, if we calculated the deviation with our first point, we would get y1 minus the true intercept plus the true slope times x1, and that would give us about sigma 1, so that, well, let's keep it purple. The chi-squared calculated from the true intercept plus the true slope times xi over sigma I squared, that would come out to be about equal to 2. Okay, and so that's the difference. I keep putting subscripts instead of superscripts for my chi-squared. And so let's say this purple one is the one based on the true values of the slope and intercept. So again, what we find is that when we calculate chi-squared using the line that's estimated from the data, we get a chi-squared value that is underestimated. When using slope and intercept based on the experimental data, we calculate, or we underestimate the true chi-squared, let's say it that way. We underestimate the true chi-squared. This is you may recall, this is something similar. We had a discussion like this when we were calculating standard deviation. Recall standard deviation. When we calculate standard deviation of a set of data, let's call it s squared, then what it's equal to is 1 over n minus 1 times, I equals 1 to n of xi minus x average squared. And the reason that we had an 1 over n minus 1 instead of a 1 over n was because x average was calculated from the individual xi measurements. And therefore, that average value is artificially set to be close to the experimental data. Whereas if we calculated the true standard deviation, or the square of that, based on not x average calculated from the data, but if we somehow knew what the true mean was, then the equation for standard deviation is 1 over n. And so we divide by a smaller number for s squared to compensate for the fact that the average x bar is not independent of the measured data. So here's what you should actually do, and I'm not going to attempt a rigorous proof of this. I'm just going to give you the results. So the result is, if we fit n data points to a model with m parameters, then only n minus m of the points are independent. I'm going to define nu as n minus m, and nu is called the number of degrees of freedom. For the fit. So the expected value of chi-squared is chi-squared should be equal to this number of degrees of freedom, which is the number of data points minus the number of fit parameters. So we could try this. If you did the one parameter fit to a measurement of one data point, then n is 1 and m is 1, and you expect chi-squared to be 0, and that's exactly what we calculated. If you do a two-parameter fit, m equals 2, to two data points, you expect chi-squared to be 0, and that's what we argued it would have to be. Alternatively, this is often stated as chi nu squared, which is the reduced chi-squared. Chi-squared divided by nu should be equal to 1. This is called the reduced chi-squared. Okay, so if we have a reasonable estimate of sigma I and our theoretical model properly describes the data, we expect the reduced chi-squared to be equal 1, to about equal to 1. So if the reduced chi-squared is greater than 1, then what we have is the model does not properly capture all features of the data. Okay, so the model is inadequate or incomplete. If chi nu squared is much less than 1, we've probably overestimated the uncertainty sigma I. So with this then, what we could do is we could use chi nu squared we could use it as a goodness of fit parameter. Is a goodness of fit parameter. So now we have some kind of physical meaning attached to the minimum of chi-squared. So remember when we were thinking of doing this Taylor series expansion of chi-squared, we had these three parameters. The three unknown parameters were chi0 squared, which is the true minimum. And so now what we'd like that to be equal to, if our fit is good, is the number of degrees of freedom, the number of measurements n minus the number of parameters. The other parameter was, we called it b. It was this coefficient in front of this quadratic. And the inverse of b told us the square of the uncertainty in the parameter. So if b was large, when we moved away from the minimum, chi-squared increased rapidly, and so that would be an indication of a small uncertainty. And then the other unknown parameter was just a refined value for the best fit parameter. And so now they all have some kind of real importance attached to them. Okay, good. So that's where I'm going to stop this video. Hope you enjoyed it. Feel free to leave comments below. Thanks very much.